Welcome to the lecture on difference equations. So for a motivating example, let's consider a population of insects that reproduces daily, and let's let P of t be the size. Let's say the birth rate is some number f that could be from 0 to infinity. So a birth rate of 1/2 means that in the next time step there are 50% more insects that were born. So the birth rate could be 2 or 3 because it's possible that each insect could reproduce 3 offspring. Now, the death rate has to be between 0 and 1. It doesn't make sense if the death rate is greater than 1. So this can be modeled by a simple equation. So the change in population is the birth rate times the population minus the death rate times the population, which is just equal to f minus d times p. So this is something that you might have seen before calculus, before you ever knew what instantaneous rate of change is. You know what change in population from one day to the next is, and that's delta p. So we're assuming that time is discretized. That is, it only takes integer values like 0, 1, and 2. And there are a lot of situations where this is more natural. A lot of species can reproduce whenever, like dogs, cats, humans. There's no real particular time of day or time of year. However, other species, like insects, might reproduce on a daily basis. Maybe there's a certain time of day that they're born or that they mate. Other species are going to reproduce on a yearly basis. Maybe they breed in the spring and they give birth in the fall. Something like that, examples like this, it's not as natural to use a continuous model, such as a differential equation, if there are definitely seasonal jumps in populations. Other examples might be like cicadas. They come out, they reproduce generally once a year, or at least they flourish once a year, and your population is going to be just maybe discontinuous, something like that, rather than a smooth curve. Okay, so let's let p sub t be shorthand for just p of t, which is the population at time t. Then delta p, we're saying, is the change in population from tomorrow to the population today, and from which it follows that, well, if you solve for pt plus 1 here, you clearly get pt plus delta p. And now if we take this value up here and we plug it in for delta p, this expression becomes pt plus f minus d times pt. And we can combine that and write that as 1 plus f minus d times pt. Now notice the difference in this expression to this expression is that there's a 1 here. There's no 1 up here. So think of that as if you are like investing at a 5% rate, then your rate of change is like 0.05 times the amount that you have in the investment. But if you want to calculate how much money you have in the next time step, you don't multiply your current amount by 0.05, you multiply it by 1.05, and that's where that 1 is coming from. Okay, so if we let lambda be this big constant here, call this the finite growth rate, then we can write this equation very simply as pt plus 1 equals lambda times pt. Okay, so as an example, let's consider a population of insects that reproduces daily as before, but let's give it some parameters. Let's say that the initial population is 300, and this could be individuals, but this could also be measured in thousands or millions or something like that. Say the birth rate is 0.3 and the death rate is 0.03 and the death rate is 0.01. In this case, the finite growth rate is lambda, which is 1 plus f minus d, so that's 1.02. And it's easy to see that in day 1 there will be this is going to be the population, 1.02 times the initial population. We're assuming that we're starting on day 0. And then on day 2, the population is 1.02 squared times p naught. On day 3, the population is 1.02 cubed times p naught. And it's easy to see the pattern. In other words, there is a closed form solution, which is this thing right here. So this is called exponential growth. Now, an interesting thing with difference equations is that even for very simple models, there is frequently no closed form solutions. This is kind of an exception in this case, because this is about as easy as we can get. Okay, so what is a difference equation formally? Let's let Q be a quantity of something. Generally, you can think of this as population. That's going to be the application that we're going to see for most of these models. So Q is a quantity defined for all integers. So think of it it's a quantity defined for every day or every year. Not necessarily for half integers or for rational numbers or irrational numbers. So at every time, time, instead of going continuously, is jumping like this. And the quantity at I should say tomorrow, is some simple function of the quantity today for some function f. In the previous example, that function is just lambda times x. This is called the Malthusian model. Not sure I actually said that correctly. It's one of those words that I read all the time, but I never actually hear it pronounced. So this is a model we saw was a linear difference equation because this function here is linear. Okay, so let's compare difference equations to differential equations, some of the basic properties of them, some of the features. So difference equations, what we just saw in this lecture, we say they are discrete time and continuous space. So discrete time means that time is not on a continuum. It's for example at integer values like day 1, day 2, day 3, day 4, day 5, day 6. So that's what it means for time to be discrete. And continuous space, maybe the word space is a little misleading, but space is this quantity. So think of it as the population. That does actually not have to be a discrete value. It does not have to be like an integer. In the example we did, the population was 1.02 times their previous population. So in theory, population could be any arbitrary real number. So the quantity is continuous, time is discrete. Compare that to differential equations. For a differential equation, we say they are continuous time and continuous space. So as an exercise, can you think of a model that is discrete time and discrete space? And maybe not. These are things that we will see later in the class. We will look at Boolean models. This is where we model, for example, a gene regulatory network and the important features of the network, things like genes and proteins and enzymes, will take either one of 2 or 3 values, like off or on, present or not present, high, medium, or low, if there's 3 values. So in that case, space is discrete. It takes 2 or 3 values. And time in these models is going to be discrete, well, frequently going to be discrete as well. Not always, but so time is going to be like at every some time step, which doesn't have to be a day. It might be a fraction of a second in the Boolean case. So that's an example that we will see of a model that is discrete time and discrete space. And I'm sure there are many, many more of these. So what about a model that is continuous time and discrete space? This might be a little bit harder, because it seems like generally if time is continuous for like a differential equation, then space is as well. But what about models that predict how many earthquakes can happen in a certain amount of time? And if you've seen if you've taken a class in stochastics, or maybe even a basic class in probability, you might have seen a Poisson. Let me see if I can write this down. Actually, I'm not sure I'm spelling this right. Poisson process. This is a stochastic process that is built from a Poisson distribution, which is a discrete distribution. So the basic idea is, what if you ask how many earthquakes are expected to happen in the next, say, 10 years? And so what's the probability distribution of the number of earthquakes? Well, you would probably expect, maybe here in South Carolina, that most likely there will be, maybe I should use red for this, most likely there will be, so let me, 0, 1, 2, 3, 4, 5, and this can go on forever. So most likely there will be no earthquakes in the next 10 years. Earthquakes that we can feel. Although maybe there's almost as good of a chance that there's one earthquake. Maybe there's a small chance that there's 2 earthquakes, 3 earthquakes, and then there's really tiny chances, diminishing probabilities that there's more earthquakes. So a Poisson process, without getting into the details, is a stochastic process that gives, as an output, given some amount of time or some time interval, gives you an expected, tells you the expected number of say, rare events in that time interval. So, for example, earthquakes. So in that case, time is continuous because time is progressing on continuously, but the space or the quantity, the number of earthquakes, that can't be a fraction. That has to be a discrete value. So a natural question to ask is, which type of model do we want to use in a given situation? So our broad goals are to, given a situation that we want to model, find an appropriate model. We first have to decide generally, are we going to use a Boolean model or a differential equation or a difference equation? But once we decide that, then we still have to design the actual quantitative model. And then once we have a model, we want to know how to analyze it. So analyze models that naturally arise. So for example, let's consider 3 problems to be modeled, and let's discuss what techniques we might want to use. So the first one, we have a population with 300 insects, and it might be, again, 300,000 insects or something. It doesn't matter. 300 insects with birth rate 0.03 and death rate 0.01. So something like this, I think a difference equation is probably a natural choice, maybe more so than a differential equation, because, as we've already said, insect populations are, I guess for some insects, are going follow some, maybe a discrete time scale, say like daily or yearly, if we're looking at like the total cicada population. Okay, so for this one, let's say a difference equation. Actually, let me show the next slide. I think I asked the question, which of these are more suited for difference equations and which are for differential equations. So the first one we're saying is for difference equations. So let's write that down. Difference. What about the second one? Let P be the value of an investment of $300 with 2% fixed interest rate. So something like that, if your money's in a bank, you're going to assume that it's being compounded continuously. So I'm going to assume that your investment growth looks like that, rather than what you learned as a kid, which was, how I was taught as a kid, was you hold your money in the bank for a year, and then after the end of 1 year, you get 5% more, and it jumps up. And you hold that for a year, and then you get 5% more. And I think that's just because when I was a kid, that's what my parents told me, because you can't explain calculus to a little kid. But that's not really what happens in a bank. Your money grows continuously. So this is probably better modeled with a differential equation. So let me write that down. And notice I can't, this pen can be tricky sometimes. I can't just write DE or OD or DE because that stands for both difference and differential equations. Okay, so finally, let P be a mass of a population of bacteria that is initially 300 grams with growth rate. I don't know what that's a typo with growth with insects. I think I copy pasted something wrong. So let's cross that out with finite growth rate 1.02. So if we have a dish of bacteria, I'm going to assume that this is going to grow continuously, so that the bacteria is going to grow something like this, rather than like the insect world. So here, I'm going to also say differential. And I also can't say DIFF. So I'll say differential. Okay, so let's go over a popular population growth model. We've seen exponential growth. So that happens when we have a population that grows exponentially, and it looks something like that. It grows without bound. But realistically, that doesn't happen for more than just a short amount of time. So if you have a population of a few bunnies, then they're going to multiply rapidly, quickly, but generally they live in a habitat and that can only support so many bunnies. So you have 2 bunnies and 4 bunnies and 8 bunnies and so forth, but at some point what's going to happen, rather than just it's going to explode without bound, is that the population of bunnies is going to increase like this, and then it's going to taper off towards some natural equilibrium, which we often call M. So this might be a good model if you're just looking in the very short term for bunnies or for bacteria growth, but this is going to be a much better population model. And it can also take into account that if you start above the equilibrium, then you will decay toward it. Okay, so the big idea of this, well, actually, let's back up a little bit. So population's growth rate realistically is not constant. For exponential growth, we assume that it's some constant rate r. But really, it depends on size. We say it's density dependent. So the big idea here is that we want to analyze the per capita growth rate, delta P, so the rate of change per person. So when P is small, then we want this per capita growth rate to be large. So if the population is not fighting for food or resources, then it should be, individuals should be reproducing like normal. Now if P is large, so if the population is almost at the carrying capacity, then we expect the per capita growth rate to be very small. And if P is too large, if we are, say, beyond the carrying capacity of the habitat, then we want this thing to be less than 0. So basically, this growth rate is going to be decreasing as the population increases. So let's make some assumptions. Okay, so let's make some assumptions. Let's let R be the per capita growth rate when population is 0. Well, I really mean when population is almost 0. So the finite intrinsic growth rate, if you want to formalize it, that's R is the per capita growth rate in the limit as the population goes to 0 from the right-hand side. So basically the rate when there is no overcrowding or no competition for resources. And let's let M be the population for which the per capita growth rate is 0. So M is the equilibrium population. This is called the carrying capacity. So if we sketch this, here's what it's going to look like. So on this axis we have population P, and up here we have the intrinsic growth rate. So that's this. So when at P equals 0, that growth rate is going to be R. And then somewhere down here, when the population is big enough, this intrinsic growth rate, the y-axis, is going to be 0. So what we want to do is this population's growth rate isn't constant. So let's call this R of P. Now this is a curve that goes through this point and it goes through that point. And there's a lot of ways that can happen. So it can curve like this, it can bend like this, it can go something like this. But we're just going to assume that the growth rate decreases linearly. It's like an Occam's razor type thing. the simplest explanation is arguably the more natural one. So let's just assume that this line is straight and it goes through these 2 points like that. Okay, so here's a better picture than what I drew on the previous slide. This is the logistic equation right here. Now the equation for this line is, let's see, the slope is negative r over m, so that's this thing right here, times p, plus the y-intercept is r right here. So this is the logistic equation. And a little bit of algebra, if we factor out an r from both of these terms, well, this thing is just written down here. If we factor out an r, we can write this as delta p over p equals r times 1 minus p over m. Okay, so the logistic equation is written right here. And if we substitute in for delta p, pt plus 1 minus pt, so we put this right into delta p, and then this p on the bottom, that's just pt, because remember p is short for p of t, which is pt. So if we substitute this into here and this into the bottom, and then we multiply the bottom pt on the other side, then we get this form of the logistic equation right here. So this is the population tomorrow based on the population today. Okay, so to see if this model is reasonable, the first thing to check are some simple cases. So let's just make sure. When population is very small, so p is much smaller than m, then 1 minus p over m, that's this thing in here, is going to be approximately equal to 1, because we have 1 minus something that's very small. So in that case, this thing is approximately equal to 1, and so the population tomorrow is just the population today, pt, times 1 plus something that's almost r. So it's approximately the exponential growth equation. And that's what we expect. When population is small, it grows approximately like exponential growth. Okay, so when the population is approximately m, let's see what happens. Then 1 minus p over m is approximately 0, because this thing here is approximately 1. So if this thing here is approximately 0, then this whole thing is approximately 0, and pt plus 1, the population tomorrow, is approximately equal to the population today. So we have pt times something that's approximately 1. So both of these cases check out, as they should. So let me just ask you, what is this function, f of x, in the discrete logistic model? Remember I said that I defined a difference equation to be a function where I should probably say p, t plus 1, is some function f of the population p, t. So in that case, up here, we can see that this is just the function f. So f of x is just x times 1 plus r times 1 minus x over m. We made it a little more complicated than exponential growth, but the function actually became a lot more complicated in the process. And notice this is a nonlinear function, because if you multiply this out, there is an x squared in here. So the logistic model is indeed nonlinear. Okay, so solutions of difference equations. Said this before, difference equations, though they are very simple, often have no closed form solution. So we came up with a closed form solution, we had exponential growth, but generally this is not the case. So that said, there are simple ways to actually plot the solutions for various initial values, say a population, p naught. You can use tools like MATLAB to do this, and we will actually do that in class and on the homework. So here are some solutions. If we take the logistic equation and we actually put in actual values for things like like R and M, and then you get curves that look like this. And when I say curves, really these things should be discrete. So if you start out with a population of 4, and then the next day you get this, the next day you get this, and the next day you get this, next day you get this, something like this. And so you don't really get a smooth curve. What these curves are meant to do is they're meant to be basically an interpolation of the discrete points. But anyways, you get something in this case for different values for different initial values, you get different curves that look like this. And this looks like what the continuous logistic equation gave us when we had differential equations. Remember, in that case we had 0 and we had m, and then we had curves that look like this for population. That's what we expect. So the difference equation really is like a discrete, in this case, is a discrete version of the differential equation. Now, we will see that there are cases when this does not hold. There's phenomena that will happen for certain parameter values for difference equations that we do not see for differential equations. And we'll see that shortly. But for now, let's learn a technique that allows us to visualize the dynamics of a difference equation using a simple graphic thing that you can teach someone in middle school to do. And let's do it with an example. So consider the following difference equation. Here's one way to write it in terms of delta t. Now if you write delta t as pt plus 1 minus pt, you can rewrite this equation like this. So these things are the same equation, just written different ways. So we can numerically find the population at any day. I should probably say if we start with P naught, we could find the population of P1 and P2, so forth. And how we do that is we are going to take the actual function, this function f of pt. So this is a this is some sort of upside down parabola, and we will plot this and the line y equals x on the same axis, and then do a technique called cobwebbing. So let's show the picture. This is the final product. I'll show you actually how we got this step by step. So let's suppose that population on day 1 is equal to 1. So that's down here. Let's say this is P naught. And just to remind you, this curve is f of x, which is this thing right there. Okay, so we start at our initial population, and then to get the population at time 1, we have to evaluate f. So that's P1, so that's f of P naught. So we have to plug P naught in to f. So in other words, we have to go up to the blue curve. We have to go up to the blue curve and go right there. And now this value right here, that is P1. Okay? So now to get P2, we have to take P1 and we have to plug it back into f again. So P2 is f of P1. So to do that, we need to bring P1 down to the x-axis. So to do that, P1, we go across here until we hit the line y equals x, right there. And then we go down to wherever that is, and that point is P1. Now P2, we take this point P1 and we go up there. And this is now P2. So P3, we got to bring P2 down to the x-axis. So we start at P2 and we go over to the line y equals x. And then we go, so down here, this is P2. And then P3 is you take that value and you go up here. And this now is P3. See the pattern? So now we're going to bring that down to the axis. This is P3. P4 is this y value right here, so this height. That's P4, which if we want to bring that down to the x-axis, we go to the line y equals x, and now, oops, well let's not make that solid, let's make that dashed. P4, and you continue in this matter, and you see what happens is that you just, this is called cobwebbing, you just go up and then eventually you're going to get stuck, and you can see that you're going to end up right there. So let's see what happens if we had started up here. Suppose we had started at 12. So suppose P0 were right here. Well, then this is P0, and then P1, we have to go all the way up to the blue curve. And then for, we have to bring that to the green curve, bring that down to the blue curve, and so forth. So notice what we're doing is we're going, starting here, we're going blue, green, blue, green, blue, green, blue, green, and we dive into the center. If we do that here, we quickly dive into that center. Okay, so let's consider another difference equation. This one's almost the same as before. The only difference is instead of 0.8, now we have 1.8 here. So the 1.8 appears here. And now the main difference here is that if you actually plot, so if you plot this function, f of p of t, so that is, or f of x, maybe I should say, that is a parabola. And then the line y equals x is going to intersect that parabola left of the critical point. So that was the previous example. And in this example, it's easy to check by plugging it into like Wolfram Alpha or MATLAB or Sage, is that in this case you have a parabola that is taller and skinnier. And so when you draw the line y equals x, it intersects on the right-hand side. So in the previous example, if we started out with P0 down here, and then we went up to the blue curve, over to the line, up to the curve, and we did this cobwebbing thing, we look like that. Or if we start over here, P0, then we go up to the blue curve, over to the black curve, and then we get stuck in here. Well, over here, let's do the same thing. Let's suppose that P0 is there. So let's go up to the blue curve, over to the black, up to the blue, over to the black, up down to the blue, and look what happens. And now it's black, blue, black, blue, black, blue. It's not even clear what's going to happen. So is this ever going to converge to this point or not? Well, the truth is I didn't actually draw this very accurately. We will see this. We'll see later that there actually are values here where this does not converge, where this thing is just going to oscillate forever, and this is called chaos. But if I had drawn this better, you would get the following picture, something like this. So yes, the intersection point is to the right, but it's if you start down here, say this is P0, what happens is, so this P0, then P1 is this, which is really just on the x-axis is down there. P2 is this height, which in the if you bring it down to the x-axis, it is actually down. It's down there. P3 is P3, this height, which, and so forth. You can bring it down here, P3, and then so forth. Once you're here, once you're here, go down to the blue curve, the green curve, the blue curve, the green curve, and then you spiral in like this. So notice what's happening is the population is oscillating. It is, so your population is P0, P1, P2, but then P3, P4, P5, and it sort of goes back and forth, back and forth and converges to, in this case, 10, but it does so in a different manner than we've seen before. Okay, so to summarize, this is the last slide, several questions. Let's sketch a plot of several solution curves for the difference equations in the previous two examples. So what I mean by that is, in the first example, the population, say I think we started at 1, population increased something like this. It increased, it approached something. If you were to fit it with a curve, you would get a curve that looked like that. And it would approach a steady state solution from below. So again, you don't really have a curve, you have these discrete points, but they are monotonically increasing. So this was example 1, where we had the 0.8. In example 2, where we had that spiraling business, what we had there is, if we started out at maybe your initial population was 1, and then P1 got bigger, P2 got bigger, but then P3 got a little smaller, P4, P5, and it's going to eventually stable out, or it's going to level off, but it definitely has some oscillatory behavior. So it's something like this. The best fit line is going to look like, hard to draw this, something like that. So again, the line is just interpolation of the actual discrete points, but this is a behavior that you do not see in differential equations or in the logistic differential equation. For that, you will only see curves like this. You will never see this oscillation behavior. Now, there are more complicated differential equations whose solution curves will look like that, but you will never get it by changing the parameters, the rate constants in the logistic equation. You do for difference equations. So that's the answer. That's the resolution to the first question. So what does the spiraling behavior of the cobweb imply about the population? Well, it is that it oscillates a little bit. And you can make the case that this is actually more natural for an actual population. Because picture a bunch of foxes on an island that has a carrying capacity. What's more likely, that the population is going to increase slowly and never go above that equilibrium, or that it might overshoot a little bit, and then when there's too many foxes, then there's some starvation. They don't reproduce as much. They're not as healthy. They spend more time looking for food instead of mating. So the population decreases, and then it oscillates back and forth. Which one of these really is more natural? And the answer probably depends on the actual growth rate. If you have a population like elephants that grows really slowly, you may not have this oscillatory behavior. But if you have a population like rabbits or bunnies or foxes or insects, it's more natural probably to have some overshooting like this. And that's what we saw. When we raised that constant r, and over here, this is when r was 0.8, so the growth rate was smaller, and over here, that constant r was 1.8. Okay, so that's the second question. These are like discussion questions. How does this relate to mass spring systems? Remember from your differential equation days, maybe in your differential equation class, that when you saw mass spring systems, you had the phenomena of a system being, when there's damping, underdamped versus overdamped. Remember that? So like if, I think my favorite example of this is if you have a door, I don't know if I can sketch this, if you have a screen door that opens up, something like, oh, this is going to be a terrible sketch. Now a screen door often, I don't know if I can sketch this. So some screen doors that open and shut will have some sort of a piston device here that controls how quickly they open and shut. And if this thing is loosened, then the door will slam shut and it'll bounce back and forth, oscillate, and then it'll level off. So picture a swinging door that can swing inward and outward. If you slam it, it goes this way, this way, this way, this way, this way, and so forth. However, if you tighten this thing up, and the door has to close really slowly, if there's a lot of dampening, this is the damper, literally on the system, then when you let go of the door, it will slowly close, and it will not swing back and forth. So the first case is when we have an overdamped mass spring system. That's this oscillation case. And the second case is when you have an underdamped mass spring system. And of course, ideally, you would like to set this damper at just the right setting so it closes as quickly as possible but doesn't slam back and forth. And that is called being critically damped. So there are definitely similarities in these two qualitative behaviors of having a population oscillate versus not oscillate to mass spring systems being underdamped versus being overdamped. And I think the discussion of these three questions should probably answer the fourth question: what features about a population are highlighted in the logistic equation using difference equations that do not arise using differential equations? So this oscillation behavior, and what we'll see soon, which I think is just it's phenomenally interesting. I don't know if I said that right, but it's really cool. Is that if you actually pump up this constant more, not only do you get oscillation behavior like this, but it's actually chaotic. So the population, instead of approaching a steady state, jumps all over the place, and it can get large and small, and it's essentially random. So for larger values, you get essentially random chaotic behavior. And then for weird, special, irrational number cases, you get things like periodic behavior. You might get a behavior that perfectly oscillates up, down, up, down, up, down, up, down, and never actually converges. Or maybe it has period 4. It has something like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and something like that. And you'll see this in any power of 2, you'll get a oscillation of that period. And then for weird things like period 3, you see a few sporadic weird periods as well, but those are classified as chaotic. So this is just the introduction to chaos theory. If you take this constant and you bump it up, you get into the realm of chaos. And that's something that we will see pretty soon, and I think it's really fascinating.